If you have seen all previous modules of group theory, by now, you must have known the structure of the character table, the physical significance of reducible and irreducible representations and their use. Now, we will try to solve real chemistry problems using the concepts of group theory. Knowing the point group of a molecule is like having its genetic code. It dictates every possible physical interaction the molecule can have with light. In spectroscopy, we use the character table of that point group to apply selection rules. Every molecule belongs to a particular point group. Several qualitative aspects of its behavior can be determined from the character table of that point group. These aspects include the extent of orbital overlap and the nature of spectroscopic transitions, such as electronic and vibrational spectroscopy. A molecule can be described using different sets of basis functions, such as its atomic orbitals and atomic coordinates. These basis functions transform according to the symmetry operations of the molecule's point group. As a result, they can be assigned irreducible representations. For example, whether an electronic transition between a ground state and an excited state is allowed or forbidden depends on the symmetry of the initial and final states as well as the symmetry of the dipole operator. Similarly, each molecular vibration transforms as a specific irreducible representation which determines whether it is IR or Raman active. First, we will determine the symmetry-allowed vibrational modes of a molecule in a step-by-step manner. Now, to understand its vibrations, we will first look at its degree of freedom. It is the number of independent ways in which a system can move or store energy. Each independent coordinate is 1 degree of freedom. And vibrations are associated with the change in the coordinates. Therefore, it has a direct relation with the degree of freedom. Let's assume a particle in a space. If it can move only along a line, then its degree of freedom will be 1. If it moves on a plane, then its degree of freedom will be 2. If it can move in 3D space, then its degree of freedom will be 3. But why do we even care how many ways a system can move? It is because almost every physical property of a system depends on it. When an atom or molecule moves, it is because it possesses some amount of energy. And by analyzing its movement, we can say something about the distribution of its energy. If a molecule moves in space, then it is called translational motion, and it is associated with its kinetic energies. If it rotates, then it is due to its rotational energy, and if it vibrates, then it is due to its vibrational energy. These are the fundamental ways through which an atom or a molecule can possess its energy, or we can say its kinetic energy. It is important to note that degrees of freedom do not include bond-breaking energy, electronic excitation energy, and chemical reaction energy. These are much higher energy processes. So in short, we can say degrees of freedom describe how a molecule stores and distributes its thermal energy through motion, either by translation, rotation, or vibration, but they do not include high-energy processes like bond breaking or electronic excitation. For a molecule to find out its degrees of freedom, we will have to consider the degrees of freedom of all atoms together, not independently. For n number of atoms, the degrees of freedom is 3n. Because each atom can move along x, y, and z direction. And these motions are not independent to each other, they are coupled by bonds. For example, in carbon dioxide, oxygen atoms cannot just move randomly. Their motion is tied to carbon and leads to collective vibrations. Now, we will classify the 3n number of degrees of freedom of any molecule into translational, rotational, and vibrational modes. The first one is translational degrees of freedom. It is always 3 for a molecule. Because always the whole molecule with all the atoms moves along x, y, and z direction. They don't move independently. During translation, all atoms move together with the same velocity, so there is no relative motion between them. Here, the kinetic energy is associated with the center of mass of the entire molecule. Then coming to rotational degrees of freedom. For a nonlinear molecule, it is 3, as it can rotate along 3 axes, and for linear molecule, it is 2, because rotation along bond axis is negligible. A molecule can undergo rotation about 3 mutually perpendicular axes passing through its center of mass. But for linear molecules, the rotation about the molecular axis is 0, as the moment of inertia tends to 0. So it does contribute only to rotational degrees of freedom. The number of translational and rotational degrees of freedom are fixed for the whole molecule and are independent on the number of atoms. Collectively, it is either 6 for nonlinear molecules or 5 for linear molecules. Apart from translation and rotation, molecule can possess energy through vibrational motions. Unlike rotational and translational motion, vibrational motion depends on the number of atoms in a molecule. Vibrational degrees of freedom describe the internal motion of atoms in a molecule, where atoms oscillate about their equilibrium positions, which involve changes in bond length. Now, for a molecule with n number of atoms, there are total 3 n coordinates. So, in total, there are a maximum 3 n number of independent ways the molecule can move. This is what the degrees of freedom is. We have already described the number of translational and rotational degrees of freedom for linear and nonlinear molecules, which are 5 and 6 respectively. So the remaining numbers from 3n are associated with the vibrational motions. So for any nonlinear molecules with n number of atoms, the vibrational degrees of freedom will be 3n-6. And for linear molecules, it is 3n-5. For example, in water, which is a nonlinear molecule, it has 3 atoms, so total degrees of freedom is 9. It has 3 translational, 3 rotational, and remaining 3 are the vibrational degrees of freedom. When we say 3 vibrational degrees of freedom, these correspond to 3 independent normal modes of vibrations, such as symmetric stretching, asymmetric stretching, and bending. However, it is important to note that each independent mode of vibration can have multiple energy levels, leading to many possible transitions. And for carbon dioxide, which is a linear molecule with total 9 degrees of freedom. 5 are for translational and rotational motion. And remaining 4 are associated with independent vibrations. These 4 independent vibrational modes are symmetric stretch, asymmetric stretch, bending in one plane, and bending in perpendicular plane. Here, the 2 bending vibrations are degenerate. These numbers are fixed, but depends on the molecular geometry. Vibrational modes are not just about number of atoms, but also about symmetry and geometry. Now, a doubt may arise, for a molecule with more than 5 atoms, for example, in methane, there are total 9 independent vibrations. So, are there really 9 possible ways of vibrations? The answer is yes. Methane does have 9 vibrational degrees of freedom, but not all 9 are completely different types of vibrations. The 9 are independent vibrational coordinates. But they are not all unique in nature. Some vibrations are degenerate, having same energy, same type, but different orientation in space. They carry the same irreducible representations.